Welcome to part one of a discussion of numbers in maths and computing. To represent numbers, we want to describe some ways to say how many of something there are. So usually we're talking about numeral representations, and the easiest type is a simple tally system. If there's one thing, we make a mark, another one, we make another mark, we have a couple more, we make a mark for those. Often when we get to fives, we put a line across in some way to indicate this group of five and move on to the next five. It doesn't have to be in fives, it can be single marks all along, or some other collection of these can be separated. It doesn't matter where the marks are, it just matters how many marks there are. So if we say, hey, count to 2 on your right hand, usually you would start with your hand closed, and you may start counting with your pointer finger, you may start counting with your thumb. You could potentially start counting with any other finger that you like, as long as there's one finger showing that corresponds to 1, then the second finger you show corresponds to 2. So some sports, for instance, baseball or softball, infielders will show there are 2 out by using their pointer finger and their pinky and separate them so that people who are standing in the outfield couple of 100 feet away maybe can see very clearly that there are 2 out. So any 2 fingers corresponds to 2. Another kind of numerical representation would be Roman numerals. It's not so much where you write the letters that correspond to the numbers. There's a bit of that. It does matter. Certain things have to be in certain orders. But how many things are there, or what the characters are what matters. But there's another way that we write numbers or the numerical values are described by the actual position. And that's a later innovation, but common for us. We know how that works. We use those positional kinds of values all the time. So the place value representation is based on an integer b that's greater than 1, that we will choose as the base. In most day-to-day numerical operations, we're thinking of base 10, but there are other bases as well, and they all have the same pattern, the same structure in the way they use. So the location of a digit determines its value, and so we have the idea of the whole number portion to the left of a point or some kind of character, and then the fractional portion to the right. This is called a radix point or a radix character because in other representations, sometimes a comma is used there, other symbols get used there to distinguish the whole number part from the fractional part. But this first position to the left of whatever that dividing symbol is the b to the 0 power. So that's the first b to the 0 is 1, so this is the ones place. The next one to the left of that is b to the first, b squared, b to the third. So in a base 10 system, we have the ones place, the tens to the left of that, then the hundreds and thousands, and so on to the left. To the right of the point in base 10, a decimal point, we have the 1/10, so the tenths place, hundredths, thousandths, and so on to the right. If we have a different base, then the structure is exactly the same. The thing that changes is b changes, so the meaning of the position changes, but it's still b to the 0th power, so the ones place, then to the left of that, the b position, the b squared, b to the third, fourth, and so on. And to the right side, on the fractional portion, 1 over b, 1 over b squared, 1 over b cubed, and so on. So in base 10, a number that's written with 317, we read that as 317. It means that from right to left, we have 7 ones, 1 10, and 3 hundreds. If we had a different base, say base 8, then the rightmost position is still the ones place, so that still means 7 ones. The place to the left is now the B to the first position, which would be the 8th place, so that means there's 1 8, and the position to the left of that means that there are 3 64s. In base 10, we have the symbols, the characters 0 through 9, so there are 10 different symbols. In base 8, the symbols are 0 through 7, so there are 8 of those. Since we can't tell by looking at 317 what base that might be, we know that it has to be base at least 8 because there's the symbol 7, but it could be any larger base as well. So we will usually write the number with some kind of notification, some kind of symbol, and we will use the number with open brackets and then the base written in the symbols that we're used to, right? Using base 10 symbols, right? Write that as base 8. So this number 317, if we write a 10 there, that means 317. If we write an 8, that means this is in base 8. If we write any other value there, it's whatever the appropriate base happens to be. So let's think about counting on your fingers. Typically, we would say, okay, we have 5 fingers, we can count to 5. That's using a tally system to do the counting. But let's try to do this counting in binary, so base 2. If we close our right hand into a fist and place it with the palm facing down on your desk, so your fingers are curled underneath, we look at the pinky finger is the rightmost, so that's going to correspond to the ones place. The ring finger is the 2 to the first place, so that is the 2s. Middle finger, 2 squared, that corresponds to 4. The pointer finger, 2 to the third, corresponds to 8. And the thumb, 2 to the fourth, corresponds to 16. So if we want to count to 1, we can extend just your pinky finger. So there are 2 values. You have the finger curled under or the finger extended. And so extending just your pinky finger is 1. If we want to count 2, that means that we have 1 in the 2 spot and 0s everywhere else. So we'll pull the pinky back in and extend just the ring finger. To count to 3, that's the ring and the pinky finger. So that's 1 1 and 1 2, reading from right to left. We keep doing that, and so 4 is 1 more than that. The 2 fingers that we have extended, the ring and pinky fingers, come back in. The middle finger is extended, and that is 4. 5 would have the middle finger and the pinky finger. 6 would be the middle finger and the ring finger. And this can keep going until we have all 5 fingers extended. So looking at those binary values, if all the fingers are closed, that corresponds to the number 0. Just having the pinky finger extended is the number 1. Number 2 is just the ring finger. 3. 4 is just the middle finger. 5, middle finger and pinky finger. So what happens if all the fingers are extended? We have a 1, 2, 4, 8, and 16. And if we add all of those together, that corresponds to the number 31. So you can count to 31 in binary on just your right hand. What if we count on both hands in binary? If we close both hands in the same way and they're in front of us, so the right hand, right pinky corresponds to the ones place, the right thumb corresponds to the 16s place, so the left thumb, which is now in front of you, corresponds to 32. So 31 means all the digits on the right hand are extended, and so to count 32, we close the right hand and then just the left thumb is extended. And this can continue until we had all 10 fingers extended, and so we can think about what is that numerical value? How high can you count on both hands? Just because you can count to 31 on one hand doesn't mean that you count to 62 on both hands. You count much higher because each finger on your left hand is now 2 to the 5th, 2 to the 6th, 2 to the 7th, 2 to the 8th, and 2 to the 9th power. So there's a pattern to these. And you want to think about what that pattern looks like. What happens in terms of all 10 fingers? What if you were also going to count on your fingers and your toes? Figure out an order, right hand, left hand, maybe right foot, then left foot, and how big could you actually count if you were counting on your fingers and your toes? Not just 20, but much, much higher. Now, actually counting on your toes is a little more difficult because they're not as easy to close and extend as your fingers are, but the idea of each value being a 0 or a 1, closed or extended. We could also, if we wanted, try to count in base 3, except in base 3 we need 3 symbols. We need something 0, 1, and 2. So with your fingers, it mostly still makes sense. 0 is the fingers curled under. It's closed into the fist. A 1 would mean that you extend it so just the first knuckle is visible, so it's partially extended, and then the 2 would be fully extended. It's a little more awkward with the thumb to do that, just because of the limited mobility and the number of knuckles on the thumb, but the idea is there. You could roll it completely under, you could partially extend it, and then fully extend it for the thumb. So if you had your, say, middle finger partially extended, this would correspond to no 1s, no 3s, and 1 9. So partially extended middle finger would be the number 9. Fully extended middle finger and everything else closed under would be 2 9s, so that would be the number 18. On your hands, going with higher bases is more difficult. Most people can't extend their fingers in other than just kind of halfway and all the way. And then your thumb definitely causes some issues beyond base 3 as well. But the structure of place value systems stays exactly the same from this point on. So what we said originally, we have this dividing aspect from the whole number portion to the fractional portion. Everything to the left corresponds to the whole number part. Everything to the right corresponds to fractional portions. So we will often need to transition from one numerical representation to another numerical representation. For us, often we are going to be looking at things in binary. We will look at things in base 8, so that's called octal, and where you have the symbols 0 through 7. We have the decimal system, which is base 10, the symbols 0 through 9, and then often the hexadecimal system, which is base 16. So we need 16 different symbols, and we usually use the symbols 0 through 9, and then 10 is represented by A, and 15 by F. So we have 0 through 9 and A through F. There are other ways we could represent the symbols. This is the most common that we will use. The ideas are exactly the same. So let's say we have a binary number 10001, and we want to convert that to decimal. What we need to do is to be able to look at the ones place. There's a 1, and then no 2s, no 4s, no 8s, but a 16. And so a 1 and a 16 corresponds to 17 in the decimal system. What if we had the number 17 in base 10 and we want to convert that to base 8? So one approach, there's more than one algorithm. This is kind of a usable algorithm if we're doing this ourselves as people. We will look at other algorithms later that are easier to implement and work well, and a left to right approach for converting numbers between bases based on their actual value rather than based on what the symbols are in place. So in this case, though, we're working from left to right or right to left, but we're thinking about what symbols are there. So we have 17, and so the largest power of 8 that is not more than 17 is 8 to the first, because 8 squared is 64, so that's too big. So there is an 8 in 17, but not just one 8, there are two 8s in 17. So we're going to put a 2 in the 8's position, and then there's one more left over from that point, so a 1 in the 1's position. So 17 in base 10 is the number 2, 1 in base 8. We don't say 21, because 21 means 2 10s and 1. If we were base 8 people, we would have a name for this. It probably wouldn't be 17, because 17 means 10 and 7. And so, well, actually, I guess it means 7 and 10 in that particular order. But we wouldn't say 21 is 7 and, or 17, excuse me, is 7 and 10. If we were base 8 people, we would have some name for it, but it would be represented in symbols as 2, 1. 2 8s and 1 more. So what if we were going to convert this binary number to octal? We just did the approach of, we took the binary number, converted it to decimal, then converted the decimal to octal. So we could always do that. We can always go through the decimal portion. But the nice thing about base 2, base 8, and base 16 is they're all related, and we can convert directly without needing to go through the decimal values at all. So since a single octal digit can hold the values 0 through 7, we want to be able to represent those same values from the binary aspect. And we saw earlier that you need 3 1s to correspond to 7. It's from the right, it's a 1, a 2, and a 4, so that is 7. So it takes 3 binary digits to hold the values of 1 octal digit. So a binary digit shortened form is bits, so we're going to talk about bits most of the time. And so what happens is, as we work from right to left, sets of 3 bits hold information about the progressively higher powers of 8. So we will group the binary values into a multiple of 3 bits, And we can add some leading zeros if necessary to fill things out so that they are in blocks of 3. But we want to make sure that we would put those on the left-hand side and not somewhere else, because that would change values. So what would we do? We would take this 5-bit value, put a leading 0 so that there are 6 values, spacing them apart, a group of 3 on the right and a group of 3 on the left. The group of 3 on the right corresponds to the value 1, and then 0, 1, 0 corresponds to the number 2, and so we see that this number that we started with in binary, which we knew was 17, corresponds to this number 2, 1 in octal, which also is 17. So the groups of 3 correspond to, we have a base 2 representation that's going to be turned into a base 8 representation. And so that values 0 to 7 are each combined in 3 binary digits. So what if we wanted to convert this same number, this binary number, to hexadecimal? To convert it to hexadecimal, the same idea holds, except that a hexadecimal digit can hold all the values from 0 to 15. And it takes 4 bits to hold those values, so rather than breaking these into blocks of 3, we will break them into blocks of 4, again adding leading zeros as necessary. So the 5 bits, we add 3 leading zeros to make this a total multiple of 4 length. And separating those into the 4s just so we can see what's going on, we have 0, 0, 0, 1, and then on the left part we also have 0, 0, 0, 1. Those values both correspond to 1s, and so in base 16 this is 1, 1, which means on the rightmost one is the 1's place, the one beside it is the 16's place. And so our number, again, that we started with was 17, and what is it? It's a 1 and 16. So 16 plus 1 is the value in hexadecimal. These calculations can also involve the other symbols in the hexadecimal values. We could have the A through F, but it behaves exactly the same. When we see A, we just think, okay, that's 10 of whatever. If the A is in the 16 spot, it means there are 10 16s. So the number A0 in decimal corresponds to 160. So the hexadecimal number A0 is 10 16s, no 1s, and that's 160 decimal. Okay, but the fractional part is the part to the right-hand side of whatever dividing symbol we're using, and we're using this point here. So sometimes it's called the binary point. If it's binary in this case, in general, it's the radix point. That's radix. So let's convert this value to decimal. Well, the whole number part on the left is 1, 0. That's 2, so that's okay. We can write down the 2. It's the part on the right that we want to look at. So the first 0 means that there are no, this is 2 to the negative 1 power, or the 1/2 spot. So no 1/2s, no 1/4, but there is a 1/8. So this binary number corresponds to 2 and 1/8. And so 2 and 1/8, if we write it as a decimal in base 10, is 2.125. So this binary number corresponds to 2.125, or 2 and an 1/8. Going the other way, if we have the decimal number and we want to convert to binary, again, there are other ways to do this. We're just using a traditional kind of doing some calculations and think about what they mean. We will be more formal with algorithms later on. The whole number part of 2, this is the decimal value 2, is 1, 0. So we have, on the left-hand side, we have 1, 0. But what we have left then is this fractional part of 0.625. And 0.625 is bigger than 1/2, so there's a 1/2 in there. So that means that the very first value after our binary point is going to be a 1. And then we're going to say, okay, the 0.625, we already have a half accounted for. So we're going to subtract that and see what's left over. What's left over is 0.125. And 0.125 we just saw is 1/8. So what we have is we have, in the original decimal number, we have 2 plus a half plus an eighth. And so 2 plus a half plus an eighth is written as 1, 0, and then the point. The 1 means the half, no fourths, and an eighth. So 2.625 is 10.101. So now let's look at another example. Let's look at 7.642, and let's write that in binary. So the whole number part, again, nice and easy. 7 is 111. The fractional part is going to require a bit more work from us. So 0.642 is bigger than a half. So we're going to record that 1/2 by putting a 1 in the 1/2's position. Subtract that from the current total, and we're left then with 0.142. Well, 0.142 is between an eighth and a fourth, so we're going to record the 1/8 and subtract that from the total. That leaves 0.017 that we need to account for. So far we have the 7, 111 dot, then we have a half and an eighth, but that doesn't quite get us there. We're not to 7.642 yet. At this point, we've just made it as far as we had in the previous example. We still need to account for this 0.017. We can't pick that part up in the 16th. That's too big. 32nd is too big. But a 64th, there is a 64th in there. So we account for the 64th, we subtract that, and we now have 0.001375 that we have to pick up. That part is even further out, and even further, and further, and further, and it turns out that this number, 7.642 in decimal, to write it in binary, we have to go into a binary fraction that does not terminate. It just keeps going and going and going, because as far as powers of 2 are concerned, there's always a little bit left. No matter how far over we pick up something, and there's just a little bit more left. We go over further and get another 1, and it has to keep going. So this is a non-terminating decimal, well, not decimal, right? A non-terminating fraction representation in binary in this case. It terminates perfectly fine in decimal, but in binary it continues on. So when we want to represent numbers in Python, then we have the two fundamental number types in Python. We have the integers, and so the integers in some languages, some programming languages, have the specified number of bits, and so there's a minimum and a maximum possible value for an integer. You only have so many bits to work with, and then maybe plus or minus that corresponds to that as well. But there's a definite minimum and a definite maximum for some particular languages. If we only had 3 bits available and then the sign, the biggest number we could have would be 7, and then the smallest number we could have, if we had plus or minus, the smallest number would be -7. Of course, programming languages use many more than 3 bits, but there's still a minimum and a maximum that aren't as big as you would expect in like mathematical integers, because mathematical integers can be as big or as small as you like. Well, Python integers are implemented in a different way where we're not going to get into the details, but it's limited only by the amount of available memory. So you can have really large numbers and really big in absolute value sense, but very negative. So they're very small numbers in that sense. That are limited only by the amount of memory you have available in your computer. And so that means that the minimum and maximum in Python is going to depend on which computer you're using and its specifications. So the exact specs of that machine will determine the largest and the smallest. That's for integers. That's the whole numbers, positive and negative values. So as long as we don't have any calculations that go outside of whatever the range is for your particular computer, then the Python integers are going to behave exactly like mathematical integers. Adding things, multiplying, doing all the calculations are going to be exactly what you expect. The issues that come up the issues that come up are when we switch to decimal values or fractional values when floats get involved. And so with floats, they're similar to the idea of real numbers in mathematics, but they are completely different. And that will be the subject of our next video when we look at how Python or other programming languages represent floats, what works well, what doesn't work well, how does all of this fit together so that we can do actual calculations on things that we need. So, as usual, feel free to ask questions in the comments by email or on Discord, and have a great day.